So at equilibrium, the number of atoms present in the system is not going to change, and also the kind of atom and their number is not going to change. So energy distribution is not going to change. So entropy is not going to change. So delta S is not going to change, and this delta S is of delta S of universe. From discussion of the previous problem that we have seen, delta S of universe is equal to 0, because that's the net delta S that is going to give us the information about the spontaneity and non-spontaneity. Delta S of universe is the real parameter that gives us the information about the net change in the energy distribution. So at equilibrium, the energy distribution is not changing. So delta S of universe must be equal to 0. Fine. And inside the system, we can see that the number of atoms net are not changing. So if the number of atoms net are not changing, that means no bond is being broken, no bond is being formed. That means the interaction with the surrounding is also not there. Because if some heat is given, something will happen. Or when something will happen inside, then only heat will be given out. That means outside the scenario is going to be the same constant, and inside is also it's being constant. That's why delta S of universe at equilibrium is going to be 0. Okay. Now, for example, if we have H2O liquid, or H2O liquid at in equilibrium with H2O gas. Of course, this will be at 100 degrees Celsius. Now for this reaction, if I have to calculate delta S of system, then I have to just find out delta S of product minus delta S of reactant. Fine. Now suppose this is happening at standard conditions. Now delta S, suppose, of H2O gaseous is provided to you as 195.9 joule per Kelvin, and similarly delta S of H2O liquid is provided to you as 86.8 joule per Kelvin. Now joule per Kelvin, same as here, joule per Kelvin. So delta S of system calculation is easy. You just have to subtract this from this. So if you do this, 195.9 minus 86.8, this is going to be 109.1 joule per Kelvin. So delta S of system you have found out. Now if someone asks you what is the delta S of surrounding, then delta S of surrounding calculation is easy, because delta S of universe is 0. So delta S of surrounding plus delta S of system must be 0. So delta S of surrounding will be simply 109.1 minus 109.1 joule per Kelvin. Now this can be verified by the data of delta H of system, because as we have discussed previously, that delta S of surrounding is equal to minus delta H of system by T of surrounding. Now delta H of system in this case has been provided as delta H for this reaction is equal to 40 kilojoule per mole. Now minus times of that will be minus 40 into kilo, and surroundings temperature is taken as 25 degrees Celsius, that will be 298 Kelvin. If we find out, this will be very close to 109.1 joule per Kelvin. So experimentally, we can, using the data of delta H, we can verify that delta S of universe indeed is 0. That just reinforces our discussion before, that delta S of universe should be 0 at equilibrium. So this is important information for you. So during the course of reaction, suppose you are plotting a graph like this. On y-axis you have delta S of universe, and on x-axis you are having extent of reaction. And suppose you have been given 4 options. Suppose in one case the graph is parabolic like this. In other case the graph is kind of inverted parabolic. In third case, if the graph is constant. In the fourth case, if the graph is suppose linear like this, the axis remains the same in all the four cases. This is not delta S, I'm sorry, this is entropy of universe. Now, as we have seen and as we know that extent of reaction is increasing, that means the reaction is going forward towards completion. Now, most of the reactions do not go to completion. They acquire an equilibrium. Suppose A plus B will acquire an equilibrium C plus D, and all of A plus B will never react. This understanding you will develop in the chapter Chemical Kinetics and Chemical Equilibrium. Now, perhaps because you are studying thermodynamics, this comes first in the list, so you may not have studied Chemical Equilibrium chapter. But for that, I'm just helping you out in giving you this information that reactions generally, if C plus D is able to react to give you A plus B, then what will happen? As A plus B is reacting, C plus B is again reacting back to give you A plus B. So A plus B will never finish out. As A plus B is reacting, it is again formed by C plus D. So in that case, our equilibrium will be reached and A plus B will never be finished. So extent of reaction will never be reaching to 1. Fine. So as the extent of reaction is increasing at some fraction of this extent, at 0.5, 0.6, 0.7, equilibrium will be reached. And we have seen before that at equilibrium, the delta S becomes 0. The change in entropy is 0. Because, and we have seen and we have discussed before, in any spontaneous reaction, delta S is positive. Now, if the reaction is not going beyond the state of equilibrium, that means A plus B were 100%, they are reacting, became 90%, react further, became 80%, reacted further, became 60%, and then the reaction stopped. In the sense that there is a dynamic equilibrium. Not reaction didn't stop, I mean the reaction is occurring, but the net change is not there. That means when A and B are 60%, then the net concentration is now constant. That means the extent of reaction is 0.4. Only 40% of them reacted. Now at this stage, reaction stops. Reaction do not go further. From the concept of thermodynamics, we have developed that for any spontaneous reaction, delta S is greater than 0. Now if this reaction is not going further, that means on going further, delta S must be negative. That's why it is not going further. That means till a particular stage, delta S will be positive, like it is increasing. Till this stage, delta S has been positive. After this, the entropy will start to decrease. From this point, as you move further, the entropy is decreasing. So if as we move ahead, delta S will start to decrease. When delta S starts to decrease, then the reaction becomes non-spontaneous. That means this is the point at which equilibrium is achieved. So as the reaction proceeds, entropy was increasing, reaction was going further. Entropy was increasing, reaction was going further. Entropy increased till this point, reaction went till this point. After this point, entropy will start to decrease. That means till equilibrium is achieved, entropy was increasing. After equilibrium is achieved, reaction is not going further. That means after equilibrium, if you increase the extent of reaction, then the entropy will decrease. That's why after the stage of equilibrium, the graph of entropy must fall down. So the second graph is the most appropriate among all the four. So if you are having an entropy on y-axis and the extent of reaction on x-axis, this is how the curve will look like. Entropy will increase up till equilibrium stage. After that, it will decrease. So after that, it will be non-spontaneous. So you have to provide external assistance if you want to increase the extent of reaction. Otherwise, the reaction will not go further on its own.